Welcome back, networking enthusiasts. If you are looking to sharpen your troubleshooting skills, you are in the right place. Last time we explored connectivity testing tools, and today we are diving into the crucial realm of network performance testing. Have you ever wondered what metrics truly define network performance? What affects TCP and UDP performance in real-world scenarios, and how can you accurately measure it? In this episode, we'll answer these questions with the help of iperf3, one of the most widely used tools for performance testing. My name is Philip and I'm excited to guide you through these key concepts. Let's get started. To measure network performance, you need to understand four key metrics. The first one is bandwidth, which refers to the maximum amount of data that can be transmitted over a network link in a given period. Bandwidth is typically measured in bits per second, megabits per second, gigabits per second, and so on. Think of bandwidth as the number of lanes on a highway. The more lanes, the more cars can travel simultaneously. Throughput is often used interchangeably with bandwidth, but it's not the same thing. While bandwidth is the maximum capacity, say 1 gigabit per second, throughput is the actual amount of data successfully transmitted. So bandwidth is theoretical maximum and throughput is real-world performance, like the actual number of cars making it through the lanes, considering delays and other factors. Next is latency or delay. That's the time it takes for data packet to travel from source to destination, usually measured in milliseconds. Even on a multi-lane highway, cars still take time to reach their destination. High latency causes lag in video calls or gaming. Then we have jitter, which is the variation in packet delays. Think of it as an uneven traffic. Some cars move smoothly, others get stuck in stop-and-go traffic, leading to an inconsistent flow of cars reaching their destination at different times. Jitter impacts real-time services like video calls and gaming. Lastly, we have packet loss. That's when packets are lost during transmission. It's like cars disappearing off the road. Strange. Lost packets lead to reduced efficiency, especially for TCP-based protocols which retransmit missing packets, further reducing throughput. Let's begin with some basic TCP throughput measurements using the iperf3 tool. This tool operates in a client-server mode. One system acts as a server and the other acts as a client. I will be testing the bandwidth between two devices. The first is a single board PC with 2.5 gigabit Ethernet link. The second device is a Mac Mini connected via Wi-Fi, which also has a 2.5 gigabit per second link speed. Both devices are on the same network segment. I will go to Mac Mini and start the iperf server using the -S option, which opens the server on port 5201 TCP by default. If you want to specify a different port, you can use -P option. Next, I will run iperf in client mode from the SBC. The command will be iperf3-c to indicate the client mode, then IP of Mac Mini, then -v for verbose output. This will establish a single TCP connection to the server and start transmitting data. Results are updated every second, showing amount of data transmitted, throughput, packet retries, and congestion window size, among other details. At the end of the test, you will see a summary with the average single stream TCP throughput, CPU utilization, and the TCP congestion control algorithm in use. Mind that generating traffic above 1 gigabit per second may require significant CPU power, and single TCP stream generally uses only one CPU core. Modern network interfaces with features like TCP segmentation offload help, but CPU load can still be a limiting factor. By default, iperf measures upstream throughput, that is, from the client to the server. To measure downstream throughput, you need to use the -R option for reverse, where the server will send data to the client. This essentially measures download speed. When we run both tests, we often see the upload and download speeds do not match. This is especially true for consumer internet connections, which typically offer much higher download speeds than upload speeds. This is known as an asymmetrical link. On the other hand, links with identical upload and download speeds are called symmetrical links. In this case, we are testing a 2.5 gigabit link, but the throughput is only around 1.3-1.2 gigabits per second. This is typical as throughput, that's the actual data rate, is often lower than bandwidth, that's the maximum theoretical capacity, especially for a single TCP stream without any performance tuning. It's also possible to test bidirectional throughput, both sending and receiving data at the same time, using the bidir option. In our case, when sending and receiving simultaneously, the throughput drops significantly. This is because the Mac Mini is on Wi-Fi connection, which operates in half-duplex mode. Only one direction can communicate at a time. Ethernet, on the other hand, is full duplex, allowing simultaneous two-way communication. Think of it like a narrow bridge. In half-duplex link, only one car can cross at a time, while in full duplex, cars can cross in both directions simultaneously. What we've learned so far is network links can be symmetrical, that is same upload and download speed, or asymmetrical, that is different speeds. Links can be full duplex, that can send and receive simultaneously, or half duplex, that can only send or receive at one time. Lastly, remember that bandwidth refers to the maximum capacity of a link, while throughput is the actual data rate achieved during transmission. So, when testing network performance, always consider whether your link is symmetrical or asymmetrical, full duplex or half duplex, and what is the bandwidth of the network interface. By default, iperf test runs for 10 seconds with the results reported every second. However, short tests may not fully reflect the stability of a network connection. Brief tests might miss temporary fluctuations, performance drop due to congestion, packet loss, or bandwidth limitations. Additionally, some links may take longer to reach their maximum throughput. To extend the test duration, you can use the -t option, which specifies the test length in seconds. For example, to run a test for 1 hour, you would use -t 3600. This time I will run an iperf test to another SBC connected via 1 gigabit Ethernet. On the remote node, I will start the iperf server and run the iperf client from the local node. Longer tests, like the 1 hour test, are more likely to reveal intermittent bandwidth drops that may go unnoticed in a 10-second test. You can also adjust the reporting interval with the -i option. For instance, to see the results every 100 milliseconds, you use -i 0.1. This increased granularity is useful when fine-tuning network parameters, such as buffer sizes, since frequent reporting gives immediate feedback on how changes impact throughput and latency. This helps optimize performance in real time. In summary, the test duration and reporting interval are valuable tools that help troubleshoot and evaluate network performance over extended periods, offering deeper insights into stability and performance trends. There are three major factors that affect TCP performance. That is, network latency, packet loss, and buffer/window size. Let's start with latency. So far, we've only measured throughput within a local network. In a well-functioning LAN using gigabit Ethernet, the round-trip time, that is the time it takes for the packet to travel to a remote host and back, is usually less than a millisecond. For a healthy Wi-Fi network, the round-trip time typically ranges from 1 to 5 milliseconds. But why does round-trip time matter? When sending data, TCP requires acknowledgement from the receiver, usually acknowledging every other packet. Round-trip time is the minimum time the sender has to wait to get feedback from the receiver on the sent data. In local networks, this latency is so low that it doesn't significantly impact performance. Let's demonstrate that by running a test to a node with 1 millisecond round-trip time. On the console, I will use the ss command to monitor key TCP statistics, while on the other console, I will run a throughput test. Here's an important metric, the congestion window size. What is that? To avoid network congestion, the sender starts with a small number of packets and gradually ramps up the data rate. This is a process known as TCP slow start. When a sender detects packet loss or delays, it adjusts the sending rate to stabilize the connection. The congestion window regulates how much data can be in flight at any moment. Data sent, but not yet acknowledged. This mechanism prevents the sender from overwhelming the network. Keep in mind that congestion window is controlled by the sender. In our test, we see the congestion window is around 500 kilobytes. This means the sender won't put more than 500 kilobytes of data on the wire without receiving an acknowledgement. This 500 kilobyte is the limit set to avoid congestion. Now, let's increase the link latency to 10 milliseconds. Let's make sure it's 10 milliseconds. And let's rerun the test. You might expect a performance drop, but the throughput remains the same. However, if you look closely, the congestion window has increased to around 1.5 megabytes. But why? When the round-trip time was just 1 millisecond, we sent half a megabyte of data and received an acknowledgement almost immediately. But with 10 milliseconds round-trip time, the sender has to wait longer for those acknowledgements, which would lead to idle time. To keep the data flowing smoothly, the sender increases the amount of data in flight to avoid sitting idle. Let's push the delay even further to 30 milliseconds and rerun the test. Now the situation changes. The throughput starts low and climbs slowly, but we hit packet loss and retransmissions. The sender then backs off, reducing the throughput before climbing again. This sawtooth pattern shows the struggle between increasing throughput and encountering network congestion. In summary, latency affects network performance. The higher the latency, the more data must be in flight to fully utilize the link capacity. But with higher latencies, the chances of packet loss and retransmissions also increase, limiting performance. Moreover, there is a greater chance of overflowing the TCP receive buffer on the recipient side. Another important metric to examine is the receive window advertised by the remote host. This window represents the amount of space the receiver has available in its buffer. The sender cannot send more data than this window allows, as doing so would overwhelm the receiver's buffer. The receive window is communicated by the receiver in every acknowledgement packet. In our case, it's around 4 megabytes. So, what does it tell us? The receive buffer can hold up to 4 megabytes of data without becoming overwhelmed. When a host advertises its receive window, it's signaling how much buffer space is currently available. Each TCP connection involves two buffers, a send buffer and a receive buffer. When an application wants to send data, it first places the data into the send buffer. From there, it gets transferred to the network card and then onto the wire. Similarly, when data is received, it's placed into the receive buffer, waiting for the application to process it. Linux performs buffer auto-tuning to adjust its buffer sizes accordingly to the connection needs. Each connection has different requirements, depending on factors like network conditions, so the kernel dynamically manages buffer sizes within set limits: minimum, initial, and maximum. What happens if TCP buffers are too small? TCP won't be able to send enough data to fully utilize the available bandwidth. As we discussed, higher latency requires more data to be in flight at any given time. But you are still limited by the receiver's buffer size. So what can you do? While Linux TCP buffer auto-tuning helps, it may not be enough in high latency environments. Fortunately, it's possible to manually increase the buffer size beyond the default values. Let's adjust the buffer size to 128 megabytes. First, we'll modify the kernel configuration file to increase the buffer size, then apply the changes. I'll do this for both the sender and receiver nodes. Now that we've increased the buffer sizes, let's rerun the test. I will restart the iperf server and rerun the test again. Do you see that? Performance has improved significantly. To sum up, latency and buffer size both affect TCP performance. In high latency environments, adjusting the TCP send and receive buffers to large values is critical to fully utilize available bandwidth. A larger receive buffer allows the receiver to advertise a larger receive window, enabling the sender to transmit more data before waiting for acknowledgement. This keeps the data pipeline flowing, resulting in improved performance. Packet loss is one of the most impactful factors on TCP performance. TCP is designed to ensure reliable data delivery, so when packets are lost, it triggers retransmission mechanisms and activates congestion control algorithms, which can drastically reduce throughput. Let's remove the 30 milliseconds delay and introduce 2% packet loss instead. Now, I will rerun the test. Do you see that? Even just 2% packet loss is devastating to throughput. If we were to add latency on top of this, the performance would degrade even further. Different congestion control algorithms handle packet loss differently. Some perform better than others under such conditions. For example, the BBR congestion control algorithm developed by Google can make a significant difference. Let's set the congestion control algorithm to BBR and apply the configuration. If I rerun the test, we'll see that BBR can handle 2% data loss without any issues. If you are interested in how it works, please check out my video on BBR. So far, we've been testing throughput using a single TCP stream. However, with iperf, you can increase the number of parallel streams using the -p option. Let's first remove the packet loss and rerun the test with 4 parallel TCP streams. This will establish 4 separate TCP connections, pushing data through all of them simultaneously. At the end, we'll see a summary showing the total throughput across all streams. Why use parallel streams? This approach better simulates real-world traffic, as most applications don't rely on just a single connection. Additionally, using multiple connections more accurately represents the total available bandwidth in environments where technologies like equal cost multipath, link aggregation control protocol, or multi-chassis link aggregation load balance traffic across multiple paths. Because each connection uses a different source port, there's a higher chance of them being hashed to a different path in the network. This is important because a single connection may not fully utilize the available bandwidth due to factors like TCP window size, packet loss, traffic shaping, or other network constraints. So far, we've only discussed TCP throughput measurement. To understand the behavior of real-time applications that rely on UDP traffic, such as video streaming and VoIP, we need to measure UDP performance. Unlike TCP, UDP is a connectionless protocol that doesn't handle flow control, congestion control, or retransmissions. It doesn't guarantee packet delivery, order, or error-free transmission. Because of this, it's up to the application or network infrastructure to ensure performance. Benchmarking UDP is different from TCP, as it focuses on packet loss and jitter rather than throughput alone. Let's demonstrate this. I will use iperf with the -u option for UDP and -b option to set a bitrate, say 100 megabits per second. Once the test is complete, we'll check the results on the iperf server and not on the client. What should we look for? First, packet loss. Look at the total amount and percentage of lost packets. If there's zero packet loss, then it's ideal. Second, jitter. This measures the variation in packet arrival times. Real-time traffic like video or voice requires smooth and predictable delivery. Jitter of around 50 microseconds is excellent, and generally anything below 30 milliseconds is considered acceptable. The lower, the better. Now, let's push the bitrate to 1 gigabit per second. In UDP, the sender can push 1 gigabit of traffic as it does not have to pace itself. It does not have to wait for any acknowledgement or worry about congestion. If we look at the results on the server side, we see that during the initial hit we've lost 14% of the traffic, and later we are losing over 4% of the traffic every second. The total loss is around 5%. Anything above 1% packet loss is typically bad for VoIP, video, and gaming. In other words, our network cannot handle 1 gigabit per second UDP throughput under these conditions. Lastly, iperf can output results in JSON format by using the -j option. Why would need this? Let me show you. While this isn't a detailed setup tutorial, I can make a more in-depth video if needed. For now, here's a quick overview. First, install InfluxDB, which is a time series database for storing time-stamped metrics. Then install Telegraph, a data collection agent that gathers system metrics like CPU and memory usage and stores them in various databases, including InfluxDB. Next, you need to configure Telegraph to store its data in InfluxDB. Then, we'll configure Telegraph to run an iperf test every minute for 30 seconds using its exec plugin. This plugin requires the iperf output to be in JSON format, which we achieve by adding the -j option to the iperf command. After that, let's restart Telegraph to apply the changes. Finally, I've set up Grafana to use InfluxDB as the backend for visualizing our metrics. I've created a few simple graphs. Throughput from client to server, round trip time, congestion window size, and receive window size, and number of retransmissions. Why is this useful? Visualizing the result using Grafana by turning raw data into clear graphs will help you identify network trends and potential issues over time. Before we wrap up, a few important considerations. When performing these tests in production environments, always run them outside of business hours to avoid impacting production traffic or getting skewed results due to network congestion. For high bandwidth applications, you can consider enabling jumbo frames by increasing the MTU from the default 1500 bytes to 9000 bytes. I've covered this in more detail in a separate video, so be sure to check it out. Keep in mind that you are not just testing the host network capacity, but also the performance of all networking equipment in between, including switches, routers, and firewalls. These devices have their own buffers, and if their interfaces are oversubscribed, they will start queuing and eventually dropping packets. Also, note that Linux network settings are typically tuned for 1 gigabit links by default. If you are using 10 or 40 gigabit interfaces, you will need to fine-tune kernel parameters like TCP window size and buffer size to handle these speeds effectively. Two other key factors in optimizing network throughput are the TCP congestion control algorithm and queuing discipline. In my systems, I use fair queuing and BBR, which I found to offer great results for most use cases. Additionally, you can fine-tune your network card by adjusting the ring buffer size and enabling or disabling advanced features like large receive offload, generic receive offload, TCP segmentation offload, scatter gather IO, and checksum offloading. In the next video, we'll dive deeper into network performance testing by introducing new tools like nuttcp, qperf, and netperf. Each of these tools offer unique features for network testing, and we'll compare how they stack up against what we've covered so far. If you found this video helpful, don't forget to like, subscribe, and hit the bell so you don't miss out on the next one. Thanks for watching and stay safe.